February 16th, 1937, Wilmington, Delaware. A chemist named Wallace Carothers gets a U.S. patent number 2130948, for synthetic fibers. It covers a brand new kind of plastic that his team built from scratch, a polymer made by combining two different molecules, each with 6 carbons. They called it Nylon 6,6. DuPont owns it. The whole world wants it. And at a lab in Berlin, a German chemist named Paul Schlack reads about that patent, and he gets to work figuring out how to legally avoid it. Less than a year later, January 29th, 1938, he succeeds. He makes a polymer that performs almost the same. It looks the same, it spins the same, but it's made from a single molecule, not 2. And that is Nylon 6. And it might be the most useful patent workaround in the history of plastics. Here at Vision Miner, we print using nylon every single day. PA6, PA12, carbon fiber nylon, glass fiber nylon, high temperature nylon, you name it, we've got the nylons. Our flagship machine is actually the 22 IDEX. It's an industrial 3D printer that we build and sell, and the reason it can run all of these nylons, plus Peaks and Ultim and polycarbonate, all the way down to ABS and ASA, is the fully heated chamber. And that's really the whole game. It lets you print the highest temperature engineering polymers on the planet, and at the same time, it keeps your filament dry on the spool in the chamber while you print. On nylon, that's the difference between a part that works and a part that warps and looks horrible. So if you've ever been frustrated trying to run real nylon on a desktop printer, or you're thinking about adding a serious nylon machine to your shop floor, then head over to visionminer.com/22IDEX and book a call with our team. We help engineering teams figure this out every single day, and we'll get you set up with the right equipment. And today's video is going to show why it's so effective with Nylon 6. And frankly, the history of this material is one of the wildest polymer histories ever. So let's set the stage. Back in the 1930s, the global textile industry runs on silk. Japan controls almost all of that. And Western chemists are racing to find or invent a synthetic replacement. DuPont gets there first. Wallace Carothers leads their fundamental research lab. They literally nicknamed it Purity Hall. His team starts in 1928 and grinds for 7 long years trying to figure something out. And then, February 28th, 1935, one of his chemists, Gerard Burchett, cooks up about ½ an ounce of a new polymer. 2 monomers, each with 6 carbon atoms. One is called hexamethylenediamine and the other is adipic acid. That is the 6,6 in Nylon 6,6. DuPont patents it, and on October 27th, 1938, they announce nylon to the world. Now, you might think that the first big nylon product was women's stockings. We all know that, we've all seen that over the years, but it actually wasn't. It was toothbrushes. Dr. West's Miracle Tuft toothbrushes. July of 1938, for the first time in human history, you could brush your teeth with something that wasn't a stiff hair pulled out of the back of a wild Chinese boar. Nylon bristles, sanitary, durable, and mass-produced. The stockings actually came later. DuPont test launched them first in their hometown, Wilmington, Delaware. October 24th, 1939. 6 department stores. Clerks were standing at the hosiery counters, taking down names and addresses to make sure that only Delaware residents could buy a pair. Customers were stacked 3 deep at the counter. They sold out basically immediately. Then on May 15th, 1940, a day DuPont marked as End Day, they launched nationally. $1.25 a pair, the same price as silk. New York City alone moved over 72,000 pairs in that single day. By the end of the first year, DuPont had sold 64 million pairs. Nylon was an instant hit. DuPont basically had an overnight monopoly. Nobody in the rest of the world could touch it without paying them royalties. Now, flip over to Germany. Berlin, 1937. Paul Schlack runs the research department at a company called Aceta. It's a joint venture between IG Farben, which is the biggest chemical company in Europe, and a big German rayon producer. His job is synthetic fibers, and he's got a problem. DuPont's patent is airtight on the 6,6 chemistry. Hexamethylenediamine plus adipic acid, that's the recipe, and it's completely locked up. So Schlack does something clever. Instead of combining two different molecules, he looks for a single molecule that already has both the chemical pieces that nylon needs. An amine group on one end and an acid group on the other. The same building blocks, but one molecule. That molecule already existed. It's called caprolactam. 6 carbon atoms, there's that 6 again, but arranged in a closed ring. Now, a quick aside on what that ring actually means. If you think of a normal molecule as a chain, atoms linked end to end like beads on a string, a ring molecule is the same chain where the two ends have bonded to each other to form a closed circle. Caprolactam is 6 carbons and a nitrogen, all bonded in a closed loop. On January 29th, 1938, Schlack heats caprolactam up. The ring pops open. The molecules then snap together end to end in a long polymer chain. The same kind of material with a different recipe and also a different patent. He called it Perlon. Today, we call it Nylon 6. German patent DE 748253. DuPont's lawyers couldn't touch it. So here's where the story gets even better. DuPont and IG Farben, instead of fighting in court, they sat down and they divided up the world. DuPont got everything west of Germany, and IG Farben got everything east. A peaceful market split between two chemical giants who had just independently invented the most important new material of the 20th century. And then World War II broke out, and the deal fell apart. Now, a quick aside on where caprolactam comes from. It's actually made from a petroleum chemical called benzene. You start with benzene refined out of crude oil and run it through a few chemical steps, and then you've got caprolactam. So Nylon 6 is, at its source, an oil-based polymer. By 1943, Germany was producing 3,500 tons of Perlon a year out of a single plant in the town of Leuna. They were using it for the exact same things the Americans were using Nylon 6 for. Parachutes, glider tow cables, aircraft tire cord. 2 countries, 2 patents, 2 chemistries. The exact same material and everything except the molecular footprint. Now, after the war, the patent fight stopped mattering. The chemistry is now what mattered. Nylon 6 turned out to be cheaper to make than Nylon 6, easier to dye, better at absorbing impacts, tougher in a lot of different ways. It became one of the most produced engineering plastics on Earth. Gears, bushings, cable ties, engine covers, carpet fiber, tire reinforcement. Roughly 10 million tons a year are projected for 2027. Now, real quick, you'll hear Nylon 6 called PA6 almost everywhere in the engineering world. PA stands for polyamide. Polyamide is just the chemical name for nylon. Every nylon is a polyamide. PA6 is Nylon 6. PA12 is Nylon 12. So we'll just use PA6 from here on out. But PA6 has one famous weakness. It loves water. The amide bonds inside PA6 act like tiny little magnets for water molecules that just hang out in the air. That's called being hygroscopic. That's HYGRO. If you pick a spool of nylon out of the bag and you leave it on the shelf, it starts absorbing moisture just out of the room. And once it does, its properties change. The strength drops and the dimensions will shift. For traditional injection molding, that's totally manageable. The pellets get dried in big industrial dryers right before they go into the injection machine. For 3D printing, though, this is the whole game. Now, in the 3D printing world, Nylon 12 became the dominant powder for laser sintering. That's SLS, selective laser sintering, because Nylon 12 absorbs much less water and it prints a little more predictably. It's got less warping, less dimensional drift. But PA6 stayed the harder option, but it was stronger and stiffer, had better heat resistance, just trickier to control, more warping, etc. Now in April of 2016, that started to change. BASF launched the first commercial PA6 powder for laser sintering, co-developed with a Chinese SLS company called Farsoon. Marketed as a serious alternative to PA12 for parts that need higher heat resistance and more mechanical strength. A 2025 review in the journal Polymers compared PA6 and PA12 in additive manufacturing directly. PA6 wins on crystallinity, strength, and thermal performance, where PA12 wins on dimensional stability and moisture resistance. And that's the same trade-off that Paul Schlack would have recognized back in 1938. For filament printing, FFF or FDM, same thing, which is basically what most machines in the world and shops are these days. The answer is to keep your nylon dry. Filament drying is a non-negotiable in this material. You dry it before you print, and you keep it dry during the print. And PA6 will reward you with parts that are tougher and more heat resistant than almost anything else in the low-end engineering polymer lineup. Now, this is one of the best things about our 22 IDEX. The filament spool actually sits inside the heated chamber while it prints. So the chamber isn't just keeping the part warm for better layer adhesion and less warping, it's actively keeping the filament dry from the first layer to the last layer, no matter how long the print runs. Now, if you want to print nylon properly without fighting moisture every single day, head over to visionminer.com/materials. Every spool we ship from that entire material catalog, we can get you certificate of analysis or certificate of conformance, the COAs and COCs, and that's what aerospace companies and a lot of others always ask for. So just give us a call, shoot us an email, we'll get you set up with that. So here's the part of the story that almost nobody talks about. The same chemistry that lets Paul Schlack make nylon 6 from caprolactam, that ring that opens up and snaps together, that reaction also works in reverse. So you can take used PA6 from old carpet, old fishing nets, old industrial waste, old clothing, and chemically unzip it back into pure caprolactam monomer. And then you repolymerize that monomer into a brand new nylon 6. Same chemical purity as virgin material. A paper published in the journal Environmental Science and Technology earlier this year did the first full life cycle assessment of doing this at an industrial scale. The verdict? It works. The alkaline route using sodium hydroxide had the lowest environmental footprint of the 4 chemistries that the researchers studied. And that makes nylon 6 one of the rare engineering polymers where the words circular economy means something more specific than just a marketing slogan. The same patent workaround that gave Paul Schlack a polymer in 1938 might be the same chemistry that helps the industry close the loop by 2030. Now, if you're working with nylon, and nylon parts are part of your business, or if you're thinking about adding a real engineering polymer machine to your shop, this is the 22 IDEX, and this is the machine that we build and sell. It's got the heated chamber that handles every material you'd ever want to print, and that includes the high temp stuff like Ultim and PEEK and PPSU and all these other awesome polymers that are great for end-use parts and real products. Aerospace, automotive, defense, medical, oil and gas, motorsports, solar. All these industries are our customers every single day. When you buy a machine from us, you're not just buying a printer, you're buying the team that will help you figure out which nylon to run, how to dry it, how to dial it in, how to use it and make parts that you can actually sell. We've got a plethora of other videos on all those topics here on YouTube. So give us a call, shoot us an email. You're gonna talk to someone real here in America, and we're here to help. So thank you so much for watching. Have a positive rest of your day. Make sure you subscribe, and I'll see you on the next one.